right. So for part one, what do you wanna? Which ones do you want to talk about here? Lee. Sure. So the what I'm going to do is I'm going to start by using the fact that I know that x plus 4 is a factor. So I'm going to start by dividing that x cubed plus x squared minus 22x minus 20 by x plus 4. And since x plus 4 is degree 1 with leading coefficient of 1, I can do that division synthetically. So when I set x plus 4 equal to 0 and solve, I get negative 4. And then if I write in the coefficients for x cubed plus x squared minus 22x minus 40, and then bring the first number down, I multiply the negative 4 by the 1, write my answer in the next spot, and then add down. And just kind of continue that process here. I get this. So what I can say is my factored form is x plus 4. I know that because of I got a remainder 0, times x squared minus 3x minus 10. I know that part because that's the quotient to the division. Now there might still be some more factoring I can do here. If I look at x plus 4, I can't factor that because it's degree 1. But the x squared minus 3x minus 10, that I might be able to factor some more. So if I go back to my factoring tree, this is something that's in the quadratic form. Okay? And its leading coefficient is 1. So if it's factorable, I should be able to use the short factoring on it and find two things that multiply to give me negative 10, and then add to give me negative 3. Those two things would be negative 5 and positive 2. So my fully factored form then is x plus 4 times x minus 5 times x plus 2. And if I go to part 2, number or letter A, I'm just going to take that factored form, set equal to 0. And since it's factored, I can just set these factors equal to 0 and solve. So my three solutions would have been negative 4, positive 5, and negative 2. So part 2 should have been pretty easy if you're able to do the part 1 and get everything in factored form, right? Does that make sense, Lee, as to what we're doing there? Okay. Other questions here from this? You want to do another one? Harley? C? Sure. So we'll start this the same way, right? So I'm going to do my synthetic division. So again, I got the remainder 0 as I was expecting. Since x plus 4 is a factor, that should be what happens. So just like in part A then, my factored form is x plus 4 times x squared plus x plus 1. And now I have to check to see if x squared plus x plus 1 can factor anymore. Well, it's in the quadratic form, and its leading coefficient is 1. So if it's factorable, I should be able to find something that multiplies to give me 1 and adds to give me 1. It's not two integers that do that, though, right? So this is as good as we can do for the factoring. So to solve this, I'm just going to set each of these factors equal to 0. So that gives me -4 for one answer. And then if I wanted to solve x squared plus x plus 1 equal to 0, what would I have to use to do that? That quadratic's not factorable. We just tried to factor it a second ago, so I can't use factoring to solve it. What would I have to use instead then? The quadratic formula. So x is equal to -b plus or minus the square root of b squared minus 4ac all over 2 times a. So that gives me that when I simplify things down. And the only part that I need to worry about here is the square root of a negative. So remember, I don't leave those in my final answer. So I can pull the negative out of the square root and replace it with an I in front of the square root. So my other answer would be -1 plus or minus I square root 3 over 2. Is that okay there, Harley? Okay. So if you couldn't factor that first part in part, or couldn't finish factoring in part A, that can happen. It's okay that that happens. Should still be able to solve whatever you have left, though, in this case using the quadratic formula. Is that okay? Caden, is your hand up there? What's up? Sure. So just like the previous ones, so that works. Again, I got remainder 0. So I have x minus 1, then I have x cubed plus 2x squared plus 9x plus 18. Am I okay to there, everybody? Okay. So x cubed plus 2x squared plus 9x plus 18 has 4 terms. If I go to my factoring tree, if I'm going to factor something with 4 terms, I'd want to use grouping. So if I make 2 groups here, from the first group I can take out an x squared. From the second group I can take out a 9. And now if I notice there's x plus 2's in common to both of those, so I can factor the x plus 2's out, and that leaves me with just x squared plus 9. So there's my factored form. Notice that x squared plus 9 can't factor anymore because it's not a difference of 2 squares, that's a sum. There's no factoring pattern for the sum of 2 squares. Caden, do you feel okay there? And then the solving part, are you good with? You're good on that? Okay. The solving should be easy once it's factored, right? Oh, if you don't get 0 for a remainder, you did something wrong, because if we're telling you that that thing is a factor, then you would have had to make some mistake. It's got to give you a 0 remainder. If it doesn't, we made some kind of an error there along the way. Whether you copied something down wrong or you did some arithmetic wrong or something else. Oh, yep, that can happen, sure. Do we feel a bit better about this assignment? So nothing really super complicated was going on here, right? You just got to use a little bit of synthetic division, which we did last semester, and then a little bit of the factoring techniques that we did last semester. We haven't done anything new per se yet. We've just taken ingredients that we already knew and kind of put them together to do a kind of a new kind of problem. All right. So let's move on here. We've talked about just about everything from this assignment. So what we're going to start talking about today is, if I'm asking you to factor one of these problems, notice on each of these I had to give you one of the factors to kind of start that synthetic division process with, right? What we're going to deal with now is, what if we take this away, that extra given information? So now we're going to have to find our own, figure out our own factor to start this process with. How many choices would we have there? How many possible factors could I have if I didn't give you that piece of information in the beginning? 2? So, for example, if we ask you to factor, say, sure, yeah, it's the next section. That would be fine. So what if we ask you to factor this? And I don't give you like some factor that we already know. That means that we're going to need to find a factor on our own to start this division with, or to use the division with. Yes? How many choices would I have? How many possible factors could this thing have? Like what? Well, I mean, it's going to have 3 factors, sure, but how many possible answers would you have for each of those 3 factors? Way more than 2. More than 4. Infinitely many. So you could have, for example, x plus 1 could be a factor. So could x plus 2. So could x plus 3, x plus 4, x plus 5, x plus 6, x plus 7, x plus 8. You could have x plus a fraction, like 1/2. There's infinitely many possibilities. So this is pretty bad, right? How would I choose which ones to pick? Right now, we have no insight as to that. So right now, we have infinitely many choices. That's bad, right? So what we're going to be working on then the rest of this week is ways to kind of reduce the number of choices and give ourselves a little bit more insight as to like how we could choose a starting point or what these possible factors would look like. Okay with that plan? And we're going to do that through a series of theorems. So the first theorem we're going to talk about is called the rational roots theorem. When we say roots, this was a piece of vocabulary that we haven't talked about yet. But a root is just, what do we want to say this is? It's the... So the roots are just the values that make a polynomial evaluate to 0. They're basically the same thing as the solutions to the polynomial equation. So what the rational roots theorem says is that for a polynomial with integer coefficients, the possible rational roots are of the form plus or minus a factor from the factor of the constant term divided by a factor of the leading coefficient. So let's do an example here to kind of illustrate how we can use this theorem. So we're just going to ask, what are the possible rational roots for this polynomial we just looked at a moment ago, x cubed plus x squared minus 22x minus 40. So the first thing I want to do is identify the constant term. What's the constant term here? -40. Okay. So then what are the factors of -40? When I say factors, what do I mean? The things that divide 40, right? So give me an example. We'll actually want to list all the numbers that can divide 40. Okay, let's just worry about all the positive numbers because we'll catch the negatives with the plus or minus in the other one. 20 is a number that divides 40. Okay, what else? 10. Okay. 2. Good. 5. 4. 1. There's still some more. 8. Still one more. 6 doesn't divide 40. It's an obvious one. Not 0. 40. Obviously, anything divides itself, right? Okay. So then we also care about the leading coefficient. What's the leading coefficient in this problem? It's not 3. It's not anything with an x in it. A coefficient is a number, just a number. It's what? 1. Right? What's the number in front of the x cubed? So there's a 1 there. We don't write it down, but we understand there to be a 1 there. Okay. And what are the factors of 1 then? Just 1, right? That's the only factor of 1. Everybody feel okay here? Okay. What about another one? Oh, we're only going to worry about positives. And the reason we only need to worry about the positive ones here, Caden, is because if I look at this up here. We have this plus or minus here, so it's going to pick up all the negatives along the way for us anyway, so I don't have to worry about the negative factors. Okay with that? Okay. But yeah, you're right. -1 does also divide 1. You're right. We're only going to worry about the positive ones, though. Okay, so my possible rational zeros are going to be plus or minus, and then I'm going to take each of my factors of the constant term and divide them each by all the factors of my leading coefficient. Well, since my leading coefficient, or my factors of the leading coefficient are only one number, I really don't have a very long list here. Yeah, we'll do that as an example in just a second, Sierra. I'd be happy to do that. That's where we're going next. But I just wanted to kind of get this out of the way here first, a simple one. Okay. So how many possible rational roots do we have here? 8. Close. Remember the plus or minuses. So each one of these are really 2 possibilities. Yeah, so we have 16 possibilities. And if I have 16 possible roots, that means I would have 16 possible factors. So we went from infinitely many possible factors to have to check, which stinks, to 16. That's a heck of a big improvement, right? Now 16 is kind of still a lot, but it's way better than infinite. And we're going to see here a little bit later a way to kind of help pare that down even a bit more. All right. All right. So let's do a second example here. Looking at this polynomial. So we're doing the same thing. We're just going to identify the possible rational roots. So my constant term is, 18 or -18. It doesn't really matter which one you're going to call it here, since when we list the factors, we only care about the positives anyway. So what are our factors of 18? I think that's all of them, right? Okay. And what's my leading coefficient here? 2. And the factors of 2 are 1 and 2, right? Everybody agree with that? Okay. So my possible rational roots are plus or minus 6 over 1, plus or minus 2 over 1, plus or minus 18 over 1, plus or minus 1 over 1, plus or minus 3 over 1, plus or minus 9 over 1, and plus or minus 6 over 2, plus or minus 2 over 2, plus or minus 18 over 2, plus or minus 1 over 2, plus or minus 3 over 2, and then plus or minus 9 over 2. So notice I had to duplicate that same list now with the other possible divisor. Sierra, that's what you're asking about here, right? Okay. Now notice on this list I have some duplicates. if I reduce things, I have 6, 2, 18, 1, 3, 9. I'd get 3 again. I don't need to list it. I get 1 again. I'm not going to list it again. I get 9 again. I'm not going to list that a second time. But then I have those 3. So that should be what my answer looks like. When you report your final answer, I'd like you to remove the duplicates, as we've done here. Do we understand where what I'm saying are duplicates? Okay. All right, so what I'd like to do now is I want to use our answer from the previous example to factor this polynomial 2x cubed plus 7x squared minus 3x minus 18. So we're going to have to pick a factor to try to start this process with. What factor do you want to start with? So we have our list already, right? This is the same polynomial from the previous example. So we already have the list made. I don't want to have to redo that again. But which one do you want to start with? It's just a pure guess right now. We don't have any intuition about what would work or not. 1. Sounds good. Did that work? No, why not? That's not 0. So 1 is not going to be one that we needed. Okay. You want to pick another one? 3. Okay. Oops. 39. And then what is that? 9108. That didn't work either. You realize there's negatives also, right, guys? Because all of those are plus or minuses. Maybe let's try -2. Since notice on both of these, the positives are giving us rather large remainders. So that one does work, right? Okay. So what can I say then? Well, I have the factor x plus 2. And then I have the factor x squared plus 3x minus 9 from that stuff. Is everybody okay there? Okay. Can we factor this anymore? Sure, Sierra. Right, so when I look at this, that's the constant term, the x coefficient, the x squared coefficient. That's how we count back, right? The remainder is the thing furthest on the right, and then we count up from there. Again, if you're not sure on why I did something or where something comes from, stop me and ask. That's perfectly fine. You're probably not the only one wondering, like, wait, what? All right. So 2x squared plus 3x minus 9. 3 terms. Is it in the quadratic form? Yeah, definitely is. In fact, it's just quadratic itself, right? Okay. Notice, though, the leading coefficient is not 1. So, oh no, unfortunately, we're going to have to do the long factoring. So we need to find the 2 numbers that multiply to give me the leading coefficient times the constant term, and then add to give me that term in the middle. So what 2 things multiply to give us negative 18 and add to give us 3? Six and negative 3. Very good. Okay. Unfortunately, 6 and negative 3 does not take me straight to my factored form. What I need to do is I'm going to replace the 3x with 6x plus a negative 3x. And I'll still bring the x plus 2 down. And now I have to factor this by grouping. So I'll make my 2 groups. From the first group, I can take out a 2x. From the second group, I can take out a negative 3. And then I notice that the x plus 3's are in common. So if I factor that out, I'm left with 2x minus 3. And there's my fully factored form. Everybody okay that see that this is still really the same process as last time? All we've done is taken away that guaranteed starting spot for us. What's the problem with this method, though? Still a lot of guessing, right? Yeah, there's still a lot of choices and a lot of guessing. Can we do better? Is there a way to reduce, like we have this list that narrows things down, right? Is there a way to go straight to the things that will probably work from the list? Probably. Good. There is. How can we do that? How might we do that? Let me give you a hint. We're going to go back to yesterday, and we talked about these 3 things that were kind of equivalent information, right? Is there a way that we can easily get either the factors, the solutions, the x-intercepts, or the zeros? Well, since we're looking for factors, it's probably not going to be easily getting the factors, right? If we could do that, we would just do that. But is there a way for us to get the solutions or the x-intercepts or the zeros for the polynomial easily? There is. Which one of these 3, the solutions, the x-intercepts, or the zeros, is going to be the one that's going to be easy for us to get? And then the question would be, how would we get it so easily? Just a 1 in 3 guess at this point. So you're saying you can get the solutions easily, or the x-intercepts, or the zeros? So we're looking at either the solutions, the x-intercepts, or the zeros. The x-intercepts are going to be the one that are easy to get. How can we get them easily? You can graph the polynomial on your calculator and read the x-intercepts off of the picture. And those x-intercepts would be good choices for our start. That's a pretty good deal, right? Because the graphing calculator handles graphing pretty nicely for us. So let's look at that for this previous problem. Okay, so let me go down to this example that we were just looking at. Pull up our graphing calculator. Yes, sir. Of course. And if you have your graphing calculator with you and you'd like to follow along, I encourage you to do so. If you like to just sit back and watch, that's cool too. No big deal. So I'll give you a minute for those of you pulling out your calculator to get those out. Okay, so power those bad boys up, the graphing calculator. Where do we go on our graphing calculator if we want to graph something? What button do we have to press? The y equals button. Okay, and then where it says y1, if I have anything there, I'm just going to clear that stuff out. And I'm going to type in our polynomial exactly as it's written on our sheet of paper. So 2x cubed plus 7x squared. Oh, boogers. Minus 3x minus 18. Now, really? So I'm just going to type that polynomial into the y equals exactly as it's written. I want to make sure that anything else in my y equals menu I've gotten rid of, so just clear out any other equations that might be in there. They're just going to get in our way. Now, before I hit my graph button and take a look at the picture, I want to go and set my window. Because I want to make sure that I can see any possible x-intercept. So I'm going to press the window button, which is right next to the y equals. And what I'd like to be able to see are any of these possible rational zeros, right? So the thing that I'm going to be changing each time is going to be the x-min and the x-max. From my window, I want to pick an x-min that's smaller than the smallest possible x-intercept, or the smallest possible rational root from my list. So if I go back to my list here, come on. What's the smallest number on my list here? Okay, so plus or minus anything is two numbers. I just want the single smallest number. Negative what? Negative 18, right? That's the smallest number on the list. So I want something a little bit smaller than negative 18 for my x-min. What's the biggest number on this list? Positive 18. So I want my x-max to be a little bit bigger than positive 18. So I'll use like negative 20 and positive 20. Sound good to you guys? The y-min and y-max don't really matter. You just need to make sure that the y-min is negative and the y max is positive, because we have to see the x-axis, because that's the only really part that we care about, is where the graph is crossing that x-axis. So as long as the y min is negative and the y max is positive, it's fine. So I use negative 10 and positive 10. All right, let's hit a graph. Hit the graph button now and take a look and see what happens. So I see the graph crosses the x-axis in 3 locations. Here, here, and then here again. The problem is that this is so far away, I can't really read where it's crossing. So I'm going to zoom in a little bit. So this is negative 20. I'd say maybe that's negative 10. And then it still looks like this stuff would be inside of negative 5. You guys agree with that? So I'm going to pick negative 5 for my new x-min. Over here, this is positive 20. That would be like positive 10. That would be like positive 5. Everything over here is still inside of positive 5. So I'll pick that as my new x max. The only reason I'm changing this is because I couldn't really read where things were crossing. But I wanted to make sure I looked at the whole picture, because if I picked a very small window, it's possible stuff happened that I wouldn't be able to see. So I want to start as wide as possible and then narrow in if I need to. Does that make sense, guys? Okay. So if I look here, each of these tick marks is 1 unit. So this is, I'm at 0, negative 1. Negative 2 is an x-intercept. And then negative 3 is another x-intercept. And then if I look at the positive side, here's 1. And then it looks like halfway in between 1 and 2 is my other. Everybody agree with that? So from the graph, it looks like I have negative 3, negative 2, and then positive 1.5. These would all be good choices to start. Everybody see how nicely this is now reduced our possible list from whatever we had, 16 or some choices. Now it's really just, we know exactly which ones to pick from there, right? Because I want to find something here that also appears on this list. It doesn't matter which one I pick? No. Any of them are fine. Just find one that works. But now we're really down to 3 guesses, right? Which is much more tolerable than 16 or infinite before that. Jacob? Of course. So let's do another example from JUMP, combining these 2 ideas. So we'll use the rational roots theorem to reduce our list down, and then we'll use the calculator to further reduce that list down. Sound good to you guys? So let's say we want to factor 2x to the 4th minus 3x cubed minus 13x squared plus 6x plus 18. The first thing I'm going to do is use my rational roots theorem. So my possible rational roots are going to be the factors of 18 all over 1, and then also the factors of 18 all over 2. I'm going to skip the even ones, though, because 2 over 2, 6 over 2, and 18 over 2 are already on my list, since they reduce down to 1, 3, and 6, or 1, 3, and 9, respectively. Everybody okay there? Notice this is the same list that we had in the previous example, right? Okay. So now I'm going to go to my graph. Clear out what was in there. So I'm going to have 2x to the 4th minus 3x to the 3rd minus 13x squared plus 6x minus, oh, is it plus or minus? Oh, it's plus. Good thing I checked. Plus 18. Once I have the polynomial typed in, I'm going to press the window button that's right next to y equals and set my window as wide as I need to capture all of my possible rational roots. So the smallest rational root is negative 18, so I'll pick something a little bit smaller than that. And the biggest rational root is positive 18, so I'll pick something a little bit bigger than that. And then I'll hit graph. Okay, so it looks like all my activity is happening like in this area right here. Everybody agree with that? You can't really read where things are being crossed, so I'm going to zoom in a little. So if I looked at the left-hand side, it looks like all the activity there is happening before negative 3 or so. If I look at the right side, it's all happening before, I don't know, positive 5 or so. Everybody agree with that? So I'm just going to change this window from negative 3 to positive 5 and hit graph again. All right. When I look at the graph there, let's see, what do I see? What values do you see for the x-intercepts? Well, here's 0. Here's positive 1. There's positive 2, so this one would be, what do you think? 1.5 maybe? Okay. And again, so 0, 1, 2. That must be 3 then. You guys agree with that? Okay. And then if I look at the negative side, this is negative 1. That's negative 2. So what do you think this one is? Negative 1.5 maybe? You guys buy that? Seems reasonable. All right. So now I want to go and look at my list up above and see if anything from my graph matches up with the things on my list. So I see positive 3, and I see both positive and negative 1.5. You guys agree with that? Okay. Which one of these do you want to start with? You want to start with the decimal to do the synthetic division with?
Yeah.
I would start with 3. It just, the arithmetic's much easier, right? All right, so let's see. 2, -1, -13, 6, and 18. So there's, and Lee, just to be clear, there's nothing wrong with starting with the 1.5. I'm just looking at this and I'm going to get like some kooky decimals in here and possibly, and that doesn't seem real appealing to me when I could just do the integer. You know what I mean? But there's nothing wrong with doing it. So 6, 3, 9, -12, and then -18 gives me 0. Great. So what 2 factors do I have then? What does the fact that when I divide with +3 and I get 0 for a remainder, what does that give me? What factor needs to go there then? X minus 3. Good. And then what's going to go in the other parenthesis? Very good. 2x to the third plus 3x squared minus 4x minus 6. Everybody okay to there? Now we have some choices now, right? So we could try to factor this by hand using our factoring tree. That might or might not work. Or we could go back up here and do another division using one of these that we haven't done. What do you guys want to do? You want to do the division again? We can do that. Okay, so this is the catch here with doing the division again. So let's use -1 1/2. What numbers are going to go inside the synthetic division bar here? It's not 2, -3, -13, 6, and 18. Because we're not trying to factor that again. We're going to be using these numbers because this is the piece that we're trying to factor now. Does everybody kind of catch that? That's an important kind of takeaway. Okay. So that worked also. So now let's see, I have the x minus 3 still. From this, I'm going to have x plus 1.5. And then from this, I'm going to have 2x squared minus 4. Is everybody okay there? Yes, Nicholas. So that's this answer from before. I'm just copying it down. Good question. Now, this is probably not the way I would want to write my final answer, because I have this factor with a decimal in it. We really haven't seen that happen before, right, when we were factoring. You guys see that? In addition, our polynomial that we're factoring has no decimals in it, so it seems weird that one of the factors would have decimals in it. But if I look at the factor to the right of it, 2x squared minus 4, notice in that part, or in that factor, that there's a greatest common factor of 2 that I can factor out of that. Everybody see that? And then what I can do then is I can just multiply the 2 into this factor, and that'll get rid of the decimal for me. And that looks a lot nicer. Or a lot more intuitive, considering the polynomial that we factored had no decimals in it. It was going to be kind of weird to rewrite the factors having decimals in them. Yeah. Don't worry. We have still more things to add on that makes this thing go faster. Because there's weird things that can happen yet still that we haven't addressed.